So I have 3 dots here in space. Notice that none of them were quoted. It doesn't say the word parallel. So I don't have direction vectors. I have 3 random dots. So I'm just going to draw those 3 random dots. One is here, one is there, one is there. And I'm going to give these names so that we can write them more simply. Alright. So these 3 dots are laying in a plane, and I need to have 2 vectors that are also laying in that plane. So all I need to do is connect either A to C, A to B, or B to C. Or a reverse of any of those directions. Any of 2 of those 3 are all I need. So I'm going to be arbitrary, and I'm going to look at this diagram, and I think I like B to A and B to C the best. So the first problem is I don't have the instructions on how to go from B to C, so I'm going to need to get that. So B to C would be the coordinates of C minus the coordinates of B, which should be -1, 4, 5, subtract 3, 2, -1. -1 minus 3 is -4. 4 minus 2 is 2, and 5 minus -1 is -6. 5 minus -1 is positive 6. Okay, good. The other thing I need is B to A. That would be the coordinates of A, subtract the coordinates of B. So I would have 2, comma, -1, comma, 4. Subtract. Coordinates of B, which are 3, comma, 2, comma, -1. So 2 minus 3 is -1. -1 minus 2 is -3. And 4 subtract -1 is 5. So now I have my direction vectors. So I just need to cross product them in order to get a normal vector, and then once I have the normal, I can get my Cartesian equation. So crossing those 2 direction vectors, -4, 2, 6, -1, -3, 5. Crossing the x coordinates written again for convenience. My normal vector would be 2 times 5 is 10, subtract -18. My y coordinates would be -6, subtract -20. And my z's would be 12, subtract -2. That would be 28. -6 plus 20 is 14, and 12 minus 2 is 14. Lovely. So I'm just going to go through and I'm going to check to make sure that that actually worked out, and that this is actually perpendicular to that. 428 would be 112. 2 14s would be 28. And 6 14s would be 60, would be 84. 20 and 80 is 100, 8 and 4 is 12, 112 minus 112 is 0. So that one worked. Try the other one. 28 times -1 is -28. 14 times -3 would be -42. And 5 times 14 is 70. So -28 and -4 would be -62, -70 plus 70 is 0. So I've got it right. No problem. Okay, so to get your Cartesian equation, you need to do the normal. 14, 14, dotted with the generic point, equaling to the normal. 14, dotted with a specific point inside the plane. Well, here you have some choice. Right? I could use A because it's in the plane, or I could use B because it's in the plane, or I could use C because it's in the plane. Doesn't matter. You get to pick. So just for ease of my suffering, I'm going to go with A. I'm going to use that one. 2, 1, or -1, 4. Just because it's first, and I don't want to have to do 4 and 5 times 14. So 2, -1, 4. So I would have 28 x's plus 14 y's plus 14 z's equals 28 times 2 is 56. 14, that's -14. 14 times 4 is 40. It's 56. 28x plus 14y plus 14z is 56, and 56 is 112 minus 14 would be 98. So I'm going to pop this over the other side. 28x plus 14y plus 14z minus 98 equals 0. There's my Cartesian equation of this particular line. So now that we've done all this work to make this Cartesian equation, we should probably use it to do something. So I'm just going to check to see if this particular dot is also on the surface with these three. So the way I'm going to do that is take my x, my y, my z, I'm just going to drop them into this equation, do the arithmetic involved, and if I get this equaling 0 using that dot, then I know that it is in fact in the plane. So I'm just going to put this x here. So 28 of these plus 14 of these plus 14 of these minus 98. And I'm hoping that's 0, because if it is worth 0, then it's in the plane. 28 times 2 would be -56. That's supposed to be a plus 14. 14 times 1 is 14. 14 times 10 is 140. -98. So 14 and 140 would be 154. -98 minus negative. -98 subtract 56 would be -154, which does, in fact, equal 0. So, because I was able to plunk the xy coordinates of this dot into the Cartesian equation for the plane and get 0 as my answer, I've confirmed that -2, 1, 10 is indeed also in the plane. So if you look back, we found an example where the dot we checked was not in the plane. We found an example where the dot we checked is in the plane. We've done the vector equation of a plane, we've done the parametric equation of a plane, and we've done the Cartesian equation of a plane. The last thing we're going to do is the triple product and determining whether 3 vectors are coplanar. So I'm going to erase this and we'll talk about that, and then we're done for this section. So that's a weird word, coplanar. It's sort of tricky to explain what that means. If I were to grab any 2 vectors, say 3, -5, 6, and -7, 1, 2. So they just go off in space from the origin, however you like, and by default, right, they make a plane, right? Like I can turn this towards the camera, I think, so that they line up nicely with each other, and they define a flat surface, right, like so. Now I've got this third vector here, and I happen to have a third slot in my fingers. Some Wolverine claws going on here. So that third vector either lines up tidally with the other 2, or it does not, something like this. So the question is this third vector, the green one, is it lined up tidally with the other two, or is it sticking off in some third direction? So the way we're going to do this is we're going to first cross product these two. What that'll do, if I can get my marker knuckles going again, if I cross product these two, I will have found a normal vector that sticks straight up and down out of this configuration. If I check for my third vector then, if my hands were dexterous enough to do this, there we go. If the third vector is coplanar, then it is also perpendicular with the normal. If it is not perpendicular, then it is not coplanar with the other two. So that's the logic. If I were to write that down in words, maybe it would make a little more sense. Get a vector perpendicular to these. And we'll call it n. If this is also perpendicular to n, then it is also, then all three are coplanar. So it's just another monster exercise in multiplication of vectors. So first thing I'm going to need is my cross product in order to make this normal vector. So x, y, z, 3, negative 5, 6, negative 7, 1, 2. Copy the x for convenience. So n will be negative 5 times 2 is negative 10, subtract 6. To get my y coordinates would be negative 42 minus 6. And to get my z's would be 3 minus 35. That's negative 16 minus 48. 3 minus 35 is negative 32. Alright, so I should check just to make sure. 3 of these would be negative 48. Negative 5 of these would be negative, positive 200, 240. And 6 of these would be negative 180 and negative 16. So 40, and that leaves negative 8. This and this leaves positive 20. So something has gone wrong here. Ah, 6 times 30 is negative 1. 6 times 2 is 12. 3/16 is 48. That is 240. 6 of these is negative 180. Negative 12. Negative 8. At least 20. Negative 12. Negative 12, negative 8, and 20 are 0. Good. So it worked out. Sorry for the awkward pause there. Let's check the other one. Negative 7 of these would be 70 and 42. 1 of these. 2 of these. 70 and a 64 is leaves 6. 6 and 42 is 48 minus 48 is 0. Yep, so that one worked out as well. So I've got my good normal vector. So I've got a vector that's perpendicular to these two. There it is. If this one is also perpendicular to this, then these three vectors are coplanar. So the way I check perpendicular is I take my normal and I dot it with 3, -1, -0. And if they are perpendicular, that will give me 0. You recall that from when we first introduced the dot product. So my n would be -16, -48, -32, dotted with 3, -1, -0. 6 of these is -48. -48 and -1 is +48. 32 and 0 is 0 equals 0. That was 48 times, yeah. So -48 plus 48 is nothing equals nothing. Huzzah! So, because 0 equals 0, this vector is perpendicular to the vector that is perpendicular to those vectors. Ipso facto, all 3 of these vectors lay in the same plane. So therefore, all 3 are coplanar. All right, off to the practice problems.